In this example, we're going to consider a fan sitting on a cart. I'm going to turn that cart on by clicking the fan button. Click. That fan is going to shove air out behind the cart. So the fan is going to apply force on the air. And thinking in terms of a Newton's third law pair, that means the air will put a force on the fan. And thanks to the fact that the cart is on wheels, and we're going to just go ahead and assume that everything is frictionless, that cart will fly forward. And we're going to define the distance it flies forward, delta x, of 1.37 meters. And the time it takes for the cart to fly forward, t equals 4.17 seconds. And I want to figure out what the net force on the cart fan system is, which means I need the mass and the acceleration. In this problem, we're going to find the acceleration. The mass of the fan cart system is going to be given to us as m equals 367 grams. Now, you've been working with Newton's second law a lot, so hopefully F net equals ma is stuck in your head. If we can figure out the acceleration of this cart, we will have found the force. I see that we're given delta x and time, so change in position and time. And I know that kinematics help me relate position, velocity, acceleration, and time when acceleration is constant. So it's safe to assume constant acceleration. I'm going to write down my favorite kinematics equation. Final position equals initial position plus initial velocity times time plus 1/2 our constant acceleration times time squared. We're given delta x, and delta hides inside of it, in general, final minus initial, and I wrote that as x, so let's just call it x. But whenever you see a delta in front of something, that means final minus initial. This is final, this is initial, so if I move over x naught, then this thing here is delta x. We're starting the cart from rest, so we have no initial velocity. That term just goes to 0. And we're left with delta x equals 1/2 a t squared. Now if I solve this equation for a, I get 2x over t squared. Then I can substitute in to delta x, substitute in the numbers from the problem, 2 times 1.37 meters over 4.17 seconds squared. And if I grab my handy dandy calculator, I get 0.16 meters per second squared as my acceleration. The problem asks for the net force, so that means I'm going to take that acceleration and multiply it by my mass. And if I want to get out my force in newtons, then my mass has to be in kilograms, my acceleration meters per second squared. 367 grams, that's 0.367 kilograms times 0.16 meters per second squared. So my net force is 0.058 newtons. Now let's consider, what if we changed this problem a bit? What if we added masses to our cart until we had a new mass of 670 grams? But we're going to have the same fan, so we'll keep the same net force. But this means that we'll get a new acceleration, and it will take a new time to cover this same distance of 1.37 meters. If I wanted to find that time, I can just do this problem backwards. I could take my net force, divide by my new mass to get a new acceleration. In fact, let's go ahead and do that. So using F net equals ma, if I want acceleration, I divide by mass. So A new equals the old force divided by the new mass, 0.058 newtons, divided by 0.670 kilograms. And I get that my A new is 0.087 meters per second squared. So that's A new. And if I want to find out how long it would take to cover that same distance, then I need to look back here at this equation, but this time I'm going to solve for t. So if I want t, it's the square root of 2x over a. Just take a second, maybe pause the video, check my algebra if you want to. Multiply by 2, divide by a, take the square root. So I have t new equals the square root of 2 delta x over a new. Oh, and this should have been a delta. I got sloppy with my deltas. Equals square root of 2, 1.37 meters, divided by 0.087 meters per second squared. And when I grab my handy dandy calculator, I get that this is 5.6 seconds.